Okay. All right, I should be back, everybody. Refresh your pages. Yeah, Ben, it should be a lot of fun, man. Definitely should be a lot of fun. Page down. I'm assuming I'm back online, but let me know if I'm not. I'll wait until I get one okay to go, but let me know when I'm back online here, okay? Yeah, let me know. You're back. Everett Sensei. Okay, cool. AOS. Awesome. Good stuff. Good to know. All right, cool. Thank you, guys. Anyway, so real quickly, and I know that probably everybody watching this stream already knows what it is, but I'm going to write it down anyway, okay? Get over it. What is STEM? Something that I care about a lot, and it's something that you also should care about quite a bit. What is STEM? STEM, first of all, is an acronym, okay? It stands for, well, it's S-T-E-M. That's the acronym, okay? The first letter, S, is science. Ooh. Ho-ho. I'm going to mix up colors. That's right. Science, tech, engineering, and math. You got it. We got science. Technology. We have engineering. And we have mathematics. We've got science, technology, engineering, and mathematics. Getting right to the hard stuff. No, this is going to be a very linear class where if you guys have any questions, just stop me, okay? Science. We categorize science by, well, a simple definition is it's observing the natural world. It's using our senses to observe the things around us. I'm going to throw these into the same category here for definition. You can consider technology and engineering. Well, there you go, Demonata. Science, that's what science is. It's observing the world around us, the natural world. And it's determining what the universe is, what the cosmos is, and how it all operates. That's what science is. Technology and engineering is modifying the natural world. Modifying the natural world. So this is us changing what is natural, right? This is us going in and trying to change the world. And then mathematics. Mathematics, you can consider mathematics as models for the above. Okay? So science is observing the natural world, technology and engineering is modifying the natural world, and then mathematics are models for doing all of the above. That's how I like to separate it out, okay? And it's pretty cool. If you guys haven't heard of STEM before, now you know what STEM is. So whenever you go to college and you look for STEM majors, it's any majors that fit those categories right there. That's what STEM is. Okay, so next step. And I know this is like very, very like, who am I? What is life? Like terraforming a desert. Holy crap. Yeah, well, there you go. Exactly. So, next question. Next big question that we are going to ask and answer. How do we know what we know? Okay. You have knowledge, you know things. How do we know what we know? Is the next question we're going to ask. And I get it. It's not engineering yet. Just hold on to your horses. We're getting there, okay? We're going to take we don't know what we know. Actually, Mank, yeah, that's basically right. No. Well, it is in a sense. This is going to be the first guest, the guest philosopher that we're going to have on the stream. He goes by the name of Aristotle. Aristotle. Aristotle was around approximately in 350 BC. Yep, because that's exactly what I wanted to happen. He was around in 350 BC, around there, and he originated from Athens, Greece. Greece. Okay, a few things about Aristotle. Okay, he was a student of another philosopher. Believe it or not, a philosopher was a student of another philosopher. He was a student of Plato. And believe it or not, even though he was his student, there were many, many differences in what they believed, okay? Greece, not Georgia. No, not Georgia. Athens, not Athens, Georgia. Athens, Greece. Exactly, Threnan. And they had actually conflicting views, even though, you know, they're most commonly known for, you know, their partnership between student and teacher. They had some differences, okay? So Plato basically believed this. He believed that there were ideal forms that exist outside of the realm of the universe that we understand, okay? That makes for great learning, though. Yeah, exactly. Exactly. Plato believed that there were ideal forms that you cannot learn. They're ideal forms that every human or every conscious being inherently knows. And when we see the imperfect forms all around you, that's how you can recognize these imperfect forms. Used to recognize objects in the real world. So basically the idea is, right, if you were to see a triangle that looks like this, and then let's say that you were to see a triangle that looks like this, and then let's say you were going to see a triangle that looks like this, okay? How do we know that they are all triangles? Because they are radically different from each other. Well, what Plato says is this. He basically says, look, this triangle and this triangle and this triangle are all imperfect forms of the ideal triangle. Sure, that's the ideal triangle. Ideal. So that's the ideal triangle right there. They're all imperfect forms of the ideal triangle. It's a warm summer's evening in ancient Greece. It's a warm summer's evening. Yeah. He basically says these are all forms of the ideal triangle, and you know the ideal triangle inherently. That's knowledge that you're born with and you can't learn. So when you see these triangles, they're basically recollections or deja vus of this inherent ideal triangle that you already know when you were born. So that's Plato, but Aristotle basically said, hey man, that doesn't make any sense because new things are being invented all the time here in Athens, and it's just not right, right? And Aristotle basically says this. What Aristotle says is, no! He says we develop these forms. The ideal forms. We develop the ideal forms using our senses. So Aristotle says, no, that's not true. We don't know anything when we're born, and how we learn all of this stuff is that we see it over time. We see it and then we learn it. We see it, so maybe we'll see this triangle, for example. Oh, whoa! Undo. That's my undo button. He says that. Oh, come on. Ridiculous. He says this. He says, you see a triangle, and if that's the only triangle you've ever seen, then you probably think triangles are always going to look like that. Okay? Then maybe, let's see, you see a triangle that looks like this. And you're probably a bit confused. You have no idea what's going on because that triangle is so incredibly different than the triangle that you've already seen, and you have no idea what to call it. But then, let's say you see a triangle at an angle like this, and that's not really a good angle. And you say to yourself, oh, okay. The triangle is a triangle, and the triangle can rotate. It doesn't necessarily matter where the triangle or how the triangle is oriented in space. It's still a triangle. And then Aristotle says, okay, let's say you see a triangle that looks like this, okay? And once again, you're like, huh? What is that? I've never seen that before in my entire life. But then let's say you see another one that looks like this, and you're like, oh, okay. So now we know this. We know that a triangle only is a triangle by forming 3 vertices together with 3 planes, or 3 lines to create a plane. Okay, so that's what Aristotle says. Again, the difference here is that Plato basically says ideal forms exist, and we know these inherent ideal forms. But then Aristotle says, no, these are things that we develop over time, and eventually we get to what we believe to be an ideal form. Okay, so let me show you an example as to how we use that in engineering and science and astronomy, for example. Let's do example. Let's say one observer in the Sol system is looking at an exoplanet in the Sol system that has some strange gravitational properties, and then another observer from the Alpha Centauri system is also observing that same exact. I do too, Demonata. Let's say another observer is observing the same exoplanet from the Alpha Centauri system. Okay, so let's draw to this here. Okay, this is the exoplanet here. Okay, and let's say this is observer number 1. Okay, number 1 right here. And this exoplanet has very strange properties. Okay, what this? Oh, actually, I'm going to do something really fancy. And you're not going to let me delete. Oh, actually, I've got a shortcut for that. Boom. So exciting. Anyway, so this is, come on. This is observer numero 1. Okay? He's from the Sol system. He's from the solar system. He's from planet or sun Sol. Okay? This planet has very strange properties in the sense that it oscillates back and forth like this. Okay? It'll oscillate this direction and then this direction. Oscillate. Oh, not a quote because it's true. Oscillating exoplanet. It's oscillating. Okay? Based off of his view, he's going to see this exoplanet do the following. He's going to see the exoplanet move this way, and the exoplanet is going to increase in size. And then he's going to see it move this way, and he's going to say it decreases in size. Oh, well, that's not really a big decrease now, is it? Oh, you fool. Late professor, continue please. Kelly, you didn't miss too much. We were going over the differences in between Aristotle's point of view and Plato's point of view when it comes to observing the natural world around you. Hey, Bougie, what's going on, man? So just to clarify, since you guys are joining right now, I'm going to go back over that again. We just went over what STEM is, and you guys already know what STEM is, so I'm not going to have to go over that again. What I was going over is the difference between Aristotle and Plato and their views on how we view the natural world around us and how we develop ideas about it. Aristotle was a student of Plato. Plato believed that there were ideal forms that exist in your mind, and you were inherently born with this knowledge, and you don't have to develop this knowledge over time. And when you see imperfect forms of those ideal forms in the universe, you recognize those ideal forms as sort of recollections, right? You think, oh, that's weird, it's a deja vu, I know what that is. And you know what it is because you already have the ideal form in your mind that you're already born with. That's what Plato believed. Now, Aristotle, on the other hand, Aristotle was Plato's student, and Aristotle said, no, that's not true. We develop these ideal forms over time, okay? And the whole example that I should probably write as a note, example, Example, what is a triangle? What is a triangle? And this is the example here. So let's say that you are born right now and you see a triangle. You look at that triangle and you basically say this. Okay, all triangles are exactly this. That's what a triangle is. But then let's say you see a triangle like this. For whatever reason, let's say that you were born on the International Space Station and you decide to rotate 180 degrees along your central axis. And you see it again and you're really confused. Because you have no idea what this shape is now, right? You know what a triangle should look like, and I'll tell you what, that's not a triangle. That's something completely different from a triangle. Keeping Bougie sane. Nice. How'd it go, Bougie? How'd it go last night? You're confused, right? But then you see another triangle like this, and then you say, oh, okay, that makes sense. Triangles can have any orientation, and they can still be a triangle. But then let's say you see a triangle like this, and once again, you've lost all sanity, and you basically say, what? What is this? My life is a lie. I don't understand it at all. And you get really confused because you have no idea what it is. And then, undo please. Then you see another triangle like this, and then you say, oh, okay, so transformation and scaling doesn't matter either. And then you can finally come up with a general postulate for what you believe a triangle is. A triangle, at that point, would then just be any three vertices connected by three lines, okay? And that's all it is. So that was Aristotle's view. He basically said, no, we develop these ideal models as to what should be happening over time. Now, I did this with geometry, but it's very similar to science and mathematics, how we develop these models. And let's continue with our example here. Let's say again, we've got a nice fellow over here who's observing an exoplanet in the Sol system. Hammered crab, though I already knew that. That stinks, man. Well, I did see the soldering last night, so I hope at least that went well. And this exoplanet has weird properties. This exoplanet simply oscillates. It has really strange gravitational parameters, where it oscillates in one direction, and then it oscillates in another direction. And from the view of this guy in the Sol system, he sees this planet, and when it oscillates in this direction, it increases in size. And when it oscillates in this direction, he says it decreases in size. And he says, oh, let me do a thought bubble here. Oh, it changes size. It changes size. Of course. And then this guy goes on, oh, it changes size. Well, I actually didn't want to do dashes there. I wanted to do a thought bubble, which is kind of like a cloud, right? Oh, it changes size. And then he goes on and he develops some function of size for this planet, okay? Hey, that's pretty cool, Bougie. I think, right? Is that hot? I don't work in Celsius at all, so. And then you have another viewer in the Alpha Centauri system, okay? And he's viewer number 2. He's also observing the same exoplanet with really strange properties. And what he sees is the exoplanet is right here, and when the exoplanet oscillates, that generally the exoplanet keeps its same shape properties, but it changes direction, right? And then he says this. He basically says, oh, I got it. It changes direction, or it changes position, rather. It changes position. And then he goes on and he generates a lot of math about position. Now, obviously, since we have an omniscient view, we know what's true, right? It's just an oscillating planet. But the whole point is, this guy developed a ton of mathematical models for something that is oscillating in size, and this guy developed a ton of mathematical models for something that's oscillating in position. I'll tell you what, though, even though we know that one is omnisciently true, it doesn't matter for both. Oh, actually, here's the thing though. Both number 1 and number 2, both observers can accurately predict what's about to happen. Even though only one is right, what's about to happen locally. You see that? Even though we know that one model is right, one model is wrong, and these two guys will go to conferences and they'll fight with each other all the time about this stuff, and they have no idea what model is right. They'll go to these interstellar conferences and they just can't get it right. But it doesn't matter because their models are sound from their individual positions. They can accurately predict what's about to happen locally. This guy will say, oh, guess what? It's about to increase in size, and it will. And this guy will say, oh, no, watch, it's going to change position, and it will, okay? Both are locally accurate. Anyway, this is sort of what we do with science and mathematics and aerospace, for example. We need to take an omniscient view. We need to look at things at all angles, which is actually what I think a lot of politicians should be doing as well, looking at things at more angles than just their self-centered angle. Anyway, this is what we have to do. We need to observe from multiple angles. But it doesn't. Again, this isn't a life lesson about. All right, sounds good, Bougie. Okay, cool. Well, it sounds like it's pretty accurate then. But it doesn't matter because both models are accurate, okay? And that's what math is. Math is a model for science. We use math for models. Math is used for scientific models. And it's strange, but there's a difference, right? Because people lump math and science in together, like, oh, math is just a part of science. No, math is used for generating and creating these scientific models. Gravity does not work how we think it works, okay? If you take a look at F equals G, negative G, your gravitational constant, mass of your first body, mass of the second body, over R cubed, times your R vector, okay? Newton's law of gravity, that does not hold true when you are expanding very far out into the solar system. If you look at a galaxy, if you look at a spiral galaxy and if you look at the rate it should be at a specific location, it's wrong. Okay, and this gravity model breaks down at a lot larger scales. Now there's again a few ideas that people have. There's a few models out there that people have about this. But this, for example, is not true. What up, teacher? Am I late for class? You're a little late, but it's fine, man. No problem. You'll catch on right away for what we're doing. I'm still basically just starting up. So this model breaks down on galactic scales. It doesn't work. Oh, galactic scales. It breaks down and it doesn't work. Now again, just like these few blokes up here, there's two different models that people are using, all right? And again, in the exoplanet example, there's a model that, oh, it's changing size from this observer. And this guy says, oh, no, it's changing location from this observer. There's a few different models. There's a few different models as to, I really need a shortcut for that on my little tablet here. There's a few models for what's going on, for the fact that why Newton's gravitational law breaks down at these incredibly large scales. There's a few examples. I mean, one model, for example, is that there's mass that we just don't see there, called dark energy or dark matter. Another example is that we just don't, that this is just an approximation, right? Maybe, and I'll write that down, maybe, wow, that was a disgusting arrow, wasn't it? That was also disgusting. Okay, one line, maybe just an approximation. We might not understand gravity as well as we think we do. But, dark gravity, what? So anyway, needless to say though, Newton did do a lot of awesome things, and I'm not saying that his law of gravitation is wrong, like it works for a lot of cases, which introduces our first huge aerospace engineering powerhouse guy, powerhouse character number 1. And we're going to be going over these powerhouse characters probably once a week. Powerhouse character number 1. You guessed it, Isaac Newton. And yes, every class starts with this stuff. Get over it. Isaac Newton. Nice liquid hype. Isaac Newton. Let's go like this. He published this paper in 1687. 1687 called, and I'm not gonna go over in deep detail what the 3 laws are because I'm sure you guys already know it. I will go over it, but just not a lot of detail, right? He published the Principia Mathematica Philosopha Naturalis. As I said earlier, the principal mathematics of natural philosophy. Okay, the principal mathematics of natural philosophy. The principal mathematics of science. Again, natural philosophy is now what we consider science. Okay? I hope so, Bougie. That'd be sweet, man. I believe that it is just we don't understand gravity fully yet. I think that's more reasonable than just having matter and mass that we don't see, because we've got a lot of different methods for viewing mass out of the optical spectrum too. So anyway, he developed the principal mathematics for natural philosophy. And in this paper, he describes 3 laws, which I'm sure you guys, or 3 postulates. 3 postulates. Okay. Laws of motion, as you guys probably know it by. All right. And we got 1. Different color, actually, would probably be nice here. Different color. 1, we've got 2, and we've got 3. All right, whoever can name one of these gets 200 space coins right off the bat. Name any one. Name any one you know, and it has to be the right one, too. It's got to be the right number. I'm picky about it. Name any of them. I want to see if you guys know them, which you should. If you've taken high school physics, then you should know these laws. You should at least know one of them, at least. At least, you should know one of them. F equals ma, but Mank, do you know which one it is? Technically, Bougie, yeah. I think that there's a lot that we don't understand model-wise on a large scale, and that's what I was saying earlier. Again, math is just a model for the universe. It's not how the universe actually works. We haven't viewed the universe at all angles yet, so we really don't know. There it is. Okay, Bougie, you got it. Mank, I need the number that it is, man. Mank, it does matter to me. I'm asking. No, Mank, I'm asking, do you know them? I'm asking, do you know them in order? Because they are sequential, man. Oh, Bougie. Bougie, I'm going to have to dock you, man. No, I'm not going to dock you because I didn't dock Mank, but... Alright. Aerospace 101. Alright, well, F equals ma is the second law. Mank, I'll give you half. 100. There you go, buddy. Aerospace 101, yeah, YOLO. It's not 1. It's actually law number 2. Mank, I'm just saying, man. Like, I get it, man. That's totally what Google's for. The whole point of this class is for you to learn something, okay? So don't just sit here being like, nah, I don't want to learn it. Learn something, man. What is 1? Objects at rest. Exactly, Bougie. That is the law number 1, okay? And that's why there is an order to it. There is an order to these, okay? The first law, and I think that's all of them. Yeah, you guys got all of them. The first law, right? Objects at rest. Actually, well, there's a more general way to say this, right? Because it's not just objects at rest. It's objects in motion, too. Particles particles, because not necessarily bodies, particles with net 0 force retain, they retain current state of motion. You're teaching aerospace? Yes, I am, YOLO. Retain their current state. And that could be either moving or at rest. It doesn't necessarily just mean at rest, but yes, objects at rest stay at rest is how people typically hear this. Objects at rest stay at rest. Okay, like that. Objects at rest stay at rest. And yeah, that's what it is. It's momentum or momentum. They keep their momentum. And then, for law number 2, Newton looks into change of momentum. And he calls that a special thing called force, okay? Force is change in momentum. No, Mank. Wrong law. Force is change in momentum. That's what he calls force. So this is your momentum. But will stay at rest in motion unless acted upon. Exactly. If you have a net 0 force, you're not going anywhere. The second one, force is change in momentum. That's what he calls force, and it's quotation because force doesn't really mean anything. It's just a word, but this is what he's defining the word to be. Okay, so force is the infinitesimal change in momentum, and this is vector notation. So we're gonna go like this: force is equal to the change over time of momentum. Okay, that's what it is. You guys, that's not Newton's law. Which is equal to d over dt of mv, right? And I'm going to move this down here. Well, no, I'm going to go over this stuff later. But basically, this you can bring this to ma in some cases. All right? In some cases. Not all cases. And we're gonna oh, that's part of the lecture I have planned actually is deriving this equation from this mess here. Come on, Bougie. Oh yes, nice, Kelly. I like it. I like it. Anyway, and yes, the third law, every force has equal and an opposite reaction. What is R? R is current. Nice, man. That's pretty cool. I see the superscript show up on my thing, on my screen too. Anyway, this third law, every force has an equal opposite reaction, is called the anti-warp drive law. The anti-warp drive law. Okay. Yeah, R is resistance. What's up, Kyran? 3 rules applied by beer cans daily. Nice. It's called the anti-warp drive law, okay? Anti-warp drive because for an object to propel forward through propulsion, you got to leave something behind, right? It's every force has an equal and opposite reaction. Now, again, I need to clarify here, these are postulates, okay? They're theories, they're ideas. They're what we believe to be true, okay? And we've extensively tested them, of course, and I need to reset that counter. I'm not drinking right now. No. That counter is not true. I need to reset it. That was still from last night. But they're just postulates. They're just ideas, right? Let's just warp space-time. That'd be cool, man. They're just ideas. That's all we think they are. And again, we've tested them pretty extensively, and we think we know what's happening, but they're just postulates, okay? So keep an open mind. I know, Kelly, I know. So anyway, let's take a look at Newton's second, okay? And let's try to derive a few cool things from it. Drunk professor. Meg, that's classified, man. We can't talk about that. Sorry. All right, so let's talk about Newton's second. And we're just going to look at particles, but I'm going to call these particles objects, okay? Objects in the physical realm have momentum. Have momentum, right? They've got momentum. Okay, which is P. We're going to call that P. Actually, well, I really want to do math stuff in one color and then word stuff in another color. We're going to call that P, okay? And we define completely different things, Liquid Hype. No, Kelly, don't. Come on, man. It's secret. Jefferson second. You're ridiculous. So P is defined as this. It's the mass of your particle multiplied by the velocity vector, okay? So we're just going to put it P for a P vector there. And again, Newton's first, we're just going to call it N1. N number 1. No force. If there's no force, no change, right? This is going to be the same. But let's say that there is a change. Then we're going to have to do the following. Well, let's go like this. Okay, let's not go like that. Too far. What about a change? What about a change in momentum? And again, this is what Newton calls force. Again, force doesn't mean anything, right? Force is just a word. Jay DeMar, what's going on? Party at Jason's pad. Yeah, what's up? Why arrows over formulas? Demonata, those are vectors, okay? That's what the arrows represent. The arrows represent vectors. Yeah, basically, YOLO. Newton who? Fig Newton? Basically. You're getting more lag, Eric? Let me check. Really? I don't see a frame rate drop at all. Yeah, I don't know about that, man. So anyway, Newton calls this weird thing, he calls it force, okay? Hey, Vasily, what's up? Newton calls this weird thing force, okay? I don't sound like the Khan Academy guy, no way. Stream is nominal, that's what I thought. Trying to get this sound just balanced. Okay. Anyway, he calls this force, okay? And again, force doesn't mean anything. It's just a word, okay? What he calls it, though, is a change in momentum. Not a cross out, please. Still getting used to this tablet, so sorry. He calls it a change in momentum, right? We represent changes through time. Changes through times with derivatives. Calculus derivatives. The guy Fig Newton. All right, so let's represent that, right? So the force, and it's a vector force in Cartesian systems. Demonata, I'll get into Cartesian systems later as well and the properties of them. Force is equal to then the change over time, right? That's what d over dt is. The slight change over time of your momentum. And I'm sorry that I'm kind of requiring calculus as knowledge here, but if you don't know what a derivative is, go look it up. Or maybe I'll do like a derivative section later, I'm not too sure. But use the force! Yeah, this is what Newton calls a force, all right? It's a change in momentum, okay? Which is also just the change in the mass of the particle. Well, actually, you know what? No, let's take a step back, okay? Nobody knew what this mass was, okay? Way back when. And you know what? Yeah, because I want to take this back to what Newton had to work with, right? Newton basically knew this. dp over dt, that's exactly what it is. That's another way of writing it, YOLO Swagons. You can write it both ways. Okay. Nice, Bougie. Slap me with your ruler. Come on, Sai. Where's the ruler slaps? So anyway, he didn't know what this mass was, right? Here's what he saw, right? This is what he saw. He basically saw this. He said, okay, so we've got some constant, right? Well, actually, I should put that inside. He basically said the force, I'm going to call this, the change in time of your velocity multiplied by some constant. Some constant. He had no idea what this was, okay? But he knew this. He knew a few things he knew this. He knew that this constant changes for each object. That's about all he knew about it, right? So it's not really a constant. Some constant. It's a constant for an object, right? But that constant changed, right? When you moved on to a new object. He said, what? Why is it changing? That doesn't make any sense. Anyway, that parameter is now more commonly known as mass. Now known as mass. And we know that mass now isn't necessarily an object property, it's a particle property. I have no way of indicating a vector in my notes. It's bugging me. Just do like a subscript V or something. I don't know. But so he knows that this is now known. It's known as mass M. I'm also going to be uploading these to YouTube Demonauta. So if you can't figure it out, you can just go watch the video, and I'll give you the notes, man. I'll give you the notes here. We now know it's known as mass, and it's not an object property. It is a it's not an object property. It's a particle property, and it's all dependent on the particles and the density of your object. It's not dependent on the object itself. It's not dependent on the shape or anything like that or size. It's not what he had originally thought. We now know that it's just a density property, but this is what he thought, right? So we now know that again, it's mass, and that we call momentum. So we now know it's mass, obviously. We now lump together m times v, which is mass, equals momentum, okay? And now we got back to the same spot, right? Now we once again have P is equal to mv, and the force is equal to the change over time of this P parameter. Or now we know it as the change over time of your mass multiplied by your velocity vector. Now, the thing is, when you're taking derivatives, it depends on if something inside the derivative is a constant, if you could take it out and not worry about it. So let's go like this. If our mass is constant, if mass is constant, so for example, yeah, that's totally how you spell constant. If mass is constant, it's sort of like a satellite. If mass is constant, like a satellite, okay, then this m is just a constant, and we can take that m out, right? So we'd be able to take it out of the d over dt. So then our force equation becomes this. Force is equal to mass times d over dt of velocity. Okay, where this term is more commonly called what? It's more commonly called acceleration. Acceleration, which is subscripted by an a. So we can replace a into the equation where dv over dt exists, and we get finally the version that you see pretty commonly, which is just f is equal to ma. Okay, and vector notation for these two. Yay, we got f equals ma. We derived f equals ma. That's how you get f equals ma. Acceleration. You got it, Kelly. It's acceleration. That's how we get f equals ma. That's how we derive f equals ma. That's how he... No way. I'm not going to get to that point, Vasily. Not today, at least. And that's an entirely different thing. I'm focusing on dynamics and mechanics, not necessarily astrophysics. Well, I will, but... not right now. Change of velocity is acceleration. Yes, it is, YOLO. So that's how you derive f equals ma. That's how Newton did it. Again, he didn't know what mass was. He knew that each object had a weird constant to it that he didn't understand. And if you change your object, that constant changes. But he knew this though. He knew that this change of velocity is called acceleration, and he knew the format of this equation. But here's the thing: what if m were a vector? Whoa, mass vector. Here's the thing, though. What if mass changes, right? What if mass changes? What if mass is changing? Then we can't just take it out of the derivative, right? Mass vectors, I like it. What if mass is changing? Well, that makes things a little bit different, right? Because then we need to include it. It doesn't matter, YOLO. It can be in whatever units you want. As long as you're consistent with the rest of the problem, then your units don't matter. Yeah. Well, here's the thing, guys. This, and I should probably write that as a note, actually. So let's go like this. I'm still getting used to everything here. Let's grab this, move it down a little bit. This was not his original notation. That was not his original notation. Originally, it was quite a bit different. Oh, Bougie. Oh, Bougie. Come on, man. You're poisoning the young minds. But what if mass changes? Okay, and again, this is not how we presented it in Principia. It was a lot different in Principia. So what if mass changes then? If mass changes, let's go like this. What if mass changes? Okay, I got it. Sorry, I was trying to get my bearings. Let's start back with the equation that we know, right? It's a change in time over momentum equals d over dt of mv, your mass multiplied by your velocity vector. That's what the force is, okay? Now, mass is changing, so we're going to have to use something called the product rule. Okay? And here's how I like looking at the product rule, okay? Let's go like this. Oh, geez, Mank. Oh, that doesn't make any sense, Bougie. Oh, that doesn't make any sense. The product rule is pretty simple. It's this. The derivative with respect to something, it doesn't have to be time, but I'm just going to be using time, of A times B is equal to A times dB over dt plus dA over dt times B. That's the product rule. Yeah, you got it. Calculus time. That means we have to leave that we had. Yeah, you got it. Because think about it. The SLS or the Falcon 9 or any rocket for that reason doesn't change. It changes mass while you go up, right? So you can't really make that assumption. You can't make that assumption that mass is going to stay constant. So you're going to go like this. You can't make that assumption. So we're going to use the product rule on this equation right here. So it's going to look like this. Force is now equal to the following. Sigh. Oh my goodness. Burning fuel is most likely. Yeah, probably, Bougie. Now it's going to look like this. We've got mass times dV over dt plus dm over dt times v. Okay, that's what it is. What am I wrong about? Wait, what are you talking about? But no, but if you're burning fuel, then yeah. Like if you're leaving the Earth, that means you're burning fuel and you have a mass dot rate, so you're changing your mass still. We don't have warp drives. Oh my goodness, Demonata, you're ridiculous, man. Alright, so now we've got, thank goodness I don't have the comments displaying on screen. I really want to upload this to YouTube, so I'm glad YouTube won't be able to see all of your guys' comments. I'm just kidding, you can say whatever you want, I don't care. Yeah, if you're leaving the Earth, that means you're burning fuel, you have a mass dot rate, and then you have this term here. You're changing your mass. Anyway, let's simplify this into terms that we can all understand, right? So F is firstly equal to MA. Whoa! MA plus M dot, what kind of M is that, huh? Plus M dot V. Okay? Hey, we're not that bad. No, you guys are not that bad. Implicit differentiate, no, not yet, YOLO. Not really. I will. Yeah, Sai, we need more ruler slaps, man. Guys, so this is the standard F equals ma, right? Which is what we typically see as Newton's second, right? It's how Newton's second is represented in physics, but this isn't physics, is it? This is aerospace engineering, which means that we got mass dot, so we need to include mass dot. Lest you piss. Yeah, I know. This is Newton's second. Now this term, m dot, is called mass flow rate. And the units is mass over time. It's how fast we're burning. Just like that, mass over time. And again, now this is kind of weird, right? You think about this. All right, so a rocket has a fuel rate, right? Rocket's got a significant fuel rate. Do we need to include NASDAQ? What? No, like mass dot. M dot is the change in mass. Okay, so your change in mass significantly has it's got significance when you're calculating force. Now, I'm not going to go into too much here. Used partially. This is going to be a lot later. We got to do a ton of orbital mechanics stuff with non-changing mass first. Use partially to derive rocket equation. There are some subtleties here, obviously, right? There's things you have to keep in mind, and it's all dependent on how you determine like mass dot, for example. Because you think about it, you're like, oh wait, mass dot should be negative, right? Because you're decreasing rate, but I'm definitely not throwing a force in the negative velocity direction. Anyway, you have to break it down particle-wise, and I will go over all that stuff a lot later. Before we do anything with the rocket equation, we're firstly focusing on constant mass objects. We are not going to go into changing mass objects quite yet, okay? Introduction to Flight, cool, man. Yeah, and again, for those of you guys that had just joined, this is the book I'm basing this off of, Spaceflight Dynamics by Weasel, 3rd edition. The BMW, if you guys have heard of it, the Bate-Mueller-White, the Introduction to Astrodynamics is another one very similar to this. This is a little bit easier to read, and it's a little bit more modern. But this is what I'm basing most of this information on. Again, not really. I'm making changes, but yeah, it's dm over dt, which is, I think I had written that down, right? I'm not mistaken. Yeah, it's dm over dt, right there. That's what m dot is. So I'm going to write that on the side. dm over dt is short notation m dot. And you can actually do that with vectors too, right? So you would have dv over dt is actually v vector dot. It's just shorthand for derivatives, right? So this would actually be r double dot. And yada yada yada. You can keep going on like that. All right, so cool. That's Newton's second law. Let's see, what else do we have here? Yeah, Cartesian stuff. I like Cartesian stuff. All right, so now that we know Newton's second law, there's some caveats for Newton's second law, okay? Caveats for Newton's second. Must be in an inertial frame. What is an inertial frame? That's a question I'm asking. I'm not just saying what is an inertial frame, and I'm asking what is an inertial frame? Caveat? Well, it's like a requirement. That's the way I like looking at it, YOLO. So it's like to calculate Newton's second, you need to be in an inertial frame. So it's sort of like a requirement. It's a gotcha, right? It's like, oh, before you do this, you got to keep this in mind. Yeah, rules of thumb, exactly. So like, oh, you got to keep this in mind if you want to do this. It's got to be in an inertial frame. But what is an inertial frame? Checklist. I like that, Vasily. Checklist. That's good. Oh man, I don't know if I want to do this today. Well, I mean, I'm going to do this. Sorry, I'm thinking about something else that I would want to do. That we could do, depending on how tired you guys are afterwards. Okay. All in the same frame of well, not all in the same frame of reference. You can have a non-inertial frame and represent everything in that non-inertial frame. Inertial is not gravity. It's not gravity go low. Okay, so this is what inertial is. Inertial is either a frame entirely at rest. Whoa. At rest. Whoa, come on. Come on, get a good line. There we go. A frame entirely at rest. Actually, I don't want that line there. Sorry. No line for you. Entirely at... Come on, you. Entirely at rest. Another afternoon figuring that acceleration. Anyway, so it's either entirely at rest or no acceleration. No acceleration. In classical, the frame of reference which bodies whose net force acting upon them is well, no, so you can have an inertial frame of reference and you can have bodies in that inertial frame with forces acting upon each other. In classical physics, a frame of reference in which bodies whose net force acting upon... Oh, net force. Yeah, okay. I got you. Net force. But that's in a closed system, Mank. So if you have like an inertial... If you've got an inertial frame here... yeah. So, Mank, you are cheating quite a bit. But that's okay, man. Like, Google's there for a reason, right? Google's there to help you learn. But... Yeah, Mank. But you're not going to get any space coins if you cheat from now on. Just letting you know. I can typically tell when people like copy and paste things from Google. Anyway, so yeah, you're right. The net force would be. Yeah, sure. You can think of that. You can think of it that way, Vasily. So if you've got if you've got a person, right, and he's viewing a baseball coming flying right at his face, his frame of reference is probably his eyes, right? That's his frame of reference. Nice, Kelly. Being center of the active ship center of mass is to prevent issues with floating point rounding errors. Yeah, that makes sense. That makes sense, Kyran. That's interesting. So, inertial, again, entirely at rest or no acceleration. This is nearly impossible. This is nearly impossible to achieve. Our method for trying to get a really good inertial frame right now, the best inertial frame we're using, Google 2020, nice, man. Best inertial frame we have right now. Is the ICRS. Which is the International Celestial Reference System. That's what it stands for. International Celestial Reference System. Do any of you guys know how the ICRS is defined? Do you guys know what objects in space are used to define the International Celestial Reference System? Probably Kyran knows. But what objects are used for the International Celestial Reference System? No, not sun. Okay, so yeah, so the International Celestial Reference System. It's centered at the sun, the ICRS, but the sun is not used to define the frame. It's centered at the ICRS though, Kelly. That's absolutely right. It's not used to define the frame though. Well, it's defined by the IAU, the International Astronomical Union. It's defined not Venus, not Nibiru. Wait, I don't know what Nibiru is, so I don't know. Maybe. Oh, that's cool, Bougie. Yeah, it's the the Berry center of the sun is the center of the frame. All right, the 10th planet. Guys, the International Celestial Reference System is defined by a ton of very far distant quasars that are essentially inertial to our view. That's how the International Celestial Reference System is defined. So you got it. We've got the sun right there. Sure, that's the sun, basically. And then we've got the Berry center of the sun. And then that's where the ICRS is oriented, okay? Right? And how the ICRS is defined, Tatooine, oh my goodness. You guys are just the best students ever. How it's defined is by very far distant quasars all over the place that essentially don't move with our point of view. And there's about 160, I believe, about 160 quasars in distant space. Distant space. Define the ICRS. Define the ICRS frame. Okay. Well, I'll be damned. Well, that is the point of this stream, Kyran. So that's good. Anyway, so yeah, that's what it's defined by. It's a collection of about 160 quasars that are actively being tracked, and that's how the frame is defined, the ICRS frame. And that's one of the best inertial frames that we know, but it's still not perfect, okay? And I'm gonna change color for that. Galactic GPS use exactly. That's what it is. Yeah. Not red. It's still not perfect. And we'll go over a lot of reference frame stuff later, but it's still not perfect, okay? It's absolutely not perfect. Oh, Demonati, you got the logo for the sun. You got the little thing for the sun. That's pretty cool, man. It's not perfect, okay? Pulsars, we have timing signals, too. Well, pulsars are used... The difficult thing, though, is that... pulsars are used for timing systems in general, but then you get into relativity, right? If you were to just track pulsars at Earth, well, pulsars would appear to be running at a different rate if you were right at the solar system barycenter because of gravitation. Seems dubious at best. It's incredibly accurate because quasars don't seem like that. They don't seem to be moving a lot because they're so far in distant space. Cannot be right in this calculus if you live in the... They still make random units for measuring everything in this place. I get out of here. I know. It's weird, man. It's weird. Well, this is defined... Well, not this. So this is solar system barycenter. Solar system barycenter. Now, this is the ICRS. Okay, we also have... Oh, come on. We also have the GCRS. Okay? What do you think the GCRS stands for? We've got the ICRS, the International Celestial Reference Plane, and it doesn't really make a lot of sense. A couple milliarc seconds a century. It's the last time I checked. They basically nailed it down. A couple milliarc. There's drift though. It's like a milliarc. No, it's maybe a milliarc second a decade or something. I forget. It's a couple, I think. It's a couple milliarc seconds per something. Galactic core. Not quite. This is actually, and it's weird. It doesn't make any sense. The International Celestial Reference System shouldn't be called ICRS because it's centered in the center of the solar system, not in the center of the Earth. GCRS is actually the geocentric The geocentric celestial reference system. Okay. Not quite, Threnan, you're close. Bougie, is it really? No, Liquid Hive, that's not right. It's the GCRS, the Geocentric Celestial Reference System, and this one is centered on the Earth, and it uses the ICRS data as well. And then you've got a few other frames. Like, for example, you've got the ITRF, which is the International Terrestrial Reference Frame. And this is not inertial. This is Earth fixed. Okay, so it tracks the Earth. Earth fixed. It includes precession, nutation, and it also includes NUTAT, nutation, and it also includes internal mass movement of the Earth. This is the ITRF. Don't tell the rednecks. Okay. Now, who determines this? Who determines this system, right? Who gets to say, hey, this is what the I determines this? Who determines this? And I'm actually going to look it up so I don't butcher the name. Oh, but that's not the real name of it. Come on. Hold on a second. I gotta find the real one, right? Oh, you're not gonna give me the... Alright. Well, it's... Fine. Whatever. You win, internet, for today. I think it resides in French, and that's why I want it to be... Oh, actually, I can do that. IRS. No. Okay, I'm not going to worry about this then. It resides in French, but I'm going to give you the English version here. In France, it doesn't reside in the language. It's the IERS. The International... Whoa. The International... And yes, this is a thing. I think this is so cool. The International Earth Rotation Service. Yes, there is an International Earth Rotation Service. Yeah. Yes, because I don't know French. Yeah, I know, Kelly. Astronomers Anonymous. Sorry, Kyran. So the IAU, yeah, you got it. So this is Kyran. Kyran is absolutely right. These two, oh crap. This one is put out by the International Astronomical Union. International Astronomical. Yes, Kyran, you're right. Astronomical Union. IAU. I'm not going to go into, those guys don't go on strike, would suck the air stopper. I know, man, that would stink. Yeah, that's the thing. The International Earth Rotation Service. Kyran is right. So, the International Earth Rotation Service is the group that is in charge of realizing the frame. I'm not going to go into the details here because we'll do that a little bit later. A system is different from the frame. Okay? Very different. The ITRS is created by the IAU, where the ITRF, which realizes, in quotes, it realizes the ITRS, is released by the IERS. So there you go. The ITRS is put out by the IAU, but the ITRF, which realizes the ITRS, is created by the IERS. There you go. Pluto does matter. I agree. I agree. There, guys. What Demonato just said, that's the IERS. That's what they actually, I think that's what they actually call it in French. Anyway, what the heck are all these systems, right? What the heck are they? So, let's go into brief detail there. What is a Cartesian system? Guys, all right, just to keep you guys interested, I know that this is like a lot of baseline stuff, and it might be a bit boring. I think it's cool. A freaking International Earth Rotation Service that exists. After this, we're going to be calculating the trajectory of a ballistic missile. Yeah, Vasily, that sounds just about right. What is a Cartesian system? Can any of you guys tell me what a Cartesian system is? We've already covered a lot of awesome material today, guys, by the way. This is great. Anyway, what is a Cartesian system? Thrust the French for having a bureaucratic structures for manners. Yeah, you guys are getting the right idea, right? It's what we consider XYZ axis, right? With the center set. Well, yeah, it's a system. Yep. Nice, Bougie. A Cartesian system is basically defined by this. A Cartesian system is defined by if you take a unit length in one direction, one dimension of space, you take another unit length in another dimension of space, and then you take another unit vector in another dimension of space, right? And you keep doing that for all dimensions of the problem statement. All dimensions. What just happened? What just happened? I have no idea. You keep doing this for all dimensions. Oh, bougie. It's okay. All dimensions of your problem. Whoa. Problem environment. Environment. Cool. Coming at me dangerously fast. Anyway, the whole idea is that you can do this for any dimension in the system, and then if you were to do the same thing, it doesn't even matter on the order. If you were to take exactly one unit vector back in any direction, well, that was a horrible representation of that, so I apologize. If you take one unit vector back in all of those dimensions, you will arrive back at your starting point, okay? That's what a Cartesian system is. So basically, you look at every dimension in your problem statement, you move one unit length in that direction, and you do that for all of the dimensions, and then you move one unit length in the other direction for all of your dimensions, and if you arrive at the same exact spot, then boom, you are in a Cartesian system, my friend. Do we live in a Cartesian system? And that's a question I'm asking you. Okay, you gonna page down now, or what? Oh, did I run out of space on the page? Yeah, I ran out of space. Alright, let me start up a new page here. New page. New page, please. Continued. Um, 0 front matter 2. Some people live in a system undefined. Because time flies in only one direction. Yeah, so space-time, and well, not to mention we're also in a gravity field too. So there's time warp. There's not time warp. There's space warp. Doing very strange things, not by numbers. Yeah. So do we live in a Cartesian system? The answer is no. Do we live in a Cartesian system? And the answer is No, we do not. And the reason for that is gravity. We've got gravity, which warps space and time. Warps space and time. So I'm going to give my shout out to my boy Einstein. He's definitely he did a lot of work into gravitational warping and whatnot. Okay, that's cool, Bougie. I didn't know if it was technically considered that, but no, we don't live in an exactly Cartesian. Not exactly. Not exactly. Hard to speak. No, we're not going into that too much. I just wanted to mention, do we live in a Cartesian system? No, we do not. Okay, so here's what a Cartesian system looks like, right? Cartesian system is, again, let's say that you have an infinite line extending in any direction, in any dimension for your problem statement. Let's say that we're working in a three-dimensional problem statement, because why not? I'm sure you guys are relatively not backward flowing in time. Interesting. I have no idea. I have no idea what it is. But here's the thing. You take all of these. You define define a unit length. Unit length. Okay. Once you've defined a unit length, refer a unit length. Nth vector in each dimension of your problem statement. Hopefully, problem statement. Hopefully, I'm showing you guys a new way of looking at Cartesian systems that you haven't seen before. Again, that's kind of the point here. So you define what a unit length is, and then you refer a unit length of an nth vector, right, in each dimension. So if we have 3, let's go like this. We've got one unit length here that we're creating ourselves. We've got one unit length here that we're creating ourselves. It's an nth unit vector, but in this case, it's a 3-dimensional vector because our problem statement is 3 dimensions. We've got another unit vector right there. Okay, so boom, we've got 3 unit vectors. And then we're just going to label them. Label them. Right, so we've got an X, we've got a Y, and we've got a Z. Cool, right? That is how you define a Cartesian system. You see, all right, how many dimensions? Hey, guys, calm down. I'll give detention to both of you. Hashtag One Direction, I like it. You guys are both going to get detention if you keep acting up. Behave yourselves. Side, get out the ruler. But that's how you define a Cartesian system, right? You take every dimension. Sounds good, Bougie. Thanks for hanging out, man. Yeah, thanks for hanging out, Bougie. Always nice having you around. Have fun with the rest of your day. This is how you define a Cartesian system, right? You've got 3 axes. Well, in this case, we got 3 because there's 3 dimensions in our problem statement. Whoa. Yes, exactly. It is different. Nice. Very effective. Timeouts are also very effective. Maybe that'll be like our school detention timeouts. That'd be funny. So again, it's different for each different for each problem statement. In this case, I'm going to do it in a 3-dimensional Cartesian system. Okay. Anyway, so that's what a Cartesian system is. Now, we're gonna do something. Okay. Let's go like this. Let's go like this. Let's change the color. We're gonna model an ICBM. Modeling an ICBM. ICBM. Few things about this ICBM. Purely theoretical. We're not launching it. Launching it. Oh wait, oh crap. Launching it. We're not launching it. It's purely theoretical, we're not launching it. Thank you for the follow, by the way. ITAR! I'm watching it, don't worry. Space Heist. Guys, if you want to join in on the Space Heist, type Space Coins as a command to see how many coins you have to contribute to Space Heist, and then do Space Heist the amount of coins, just like what Kelly did. Exactly, Vasily, nice. No, not exactly YOLO, it's close. It's purely theoretical. It will not explode. Will not explode. It will not explode. Payload is going to be puppies and kittens. Kittens. Destination. Puppy and kitten world. Other assumptions, because I know you guys are gonna no Space Heist for you, Demonata. You're out of it for now. Gotcha. Some other assumptions. Puppies and kittens, because I know one of you guys are going to mention this, have plenty of oxygen. So we're going to deliver this from no Kyran. That's why I did all this stuff, so you guys don't say that. Anyway, from the USA. Okay, we got to deliver a payload of puppies and kittens to Puppy and Kitten World. Okay, we will, Vasily. We will. All right. So our problem statement. Oh yeah, Kyran. Our problem. Get these creatures home. Let's get them home, huh? So first things first. We need to define our reference system. So, a few things about our reference system, right? We need a Cartesian system to work with. Luckily for us, IERS stopped Earth's rotation for this launch. How nice of them. Stopped Earth's rotation. Also, just by chance, Earth is no longer orbiting the sun today. So what does that mean? And let's say that we're far away from any other stars too. Land of our dear eternal retriever. Hold on to something. Matt, no, we're also assuming that they are securely strapped, okay? We're assuming that these puppies and kittens are securely strapped into their spot. They're comfortably strapped, mind you. And Earth is no longer orbiting the sun today, and that means a few things, right? That means, luckily, we can consider the Earth. Ooh. And despite conspiracies, Earth, we found out that Earth is an infinitely flat plane. Luckily for us, scientists just discovered this. We just discovered this, okay? Oh, Kelly, nice. We just discovered this too. It's awesome. A lot of awesome things are happening now. Which means that we can do a few things. Which means we can define the following. We can define an inertial frame with a uniform gravity field. How neat is that? I'm so glad that scientists were able to discover this today. Uniform gravity field. Thank goodness. Well, we just discovered it today, believe it or not. So we can define an inertial frame with a uniform gravity field. How cool is that? So we've got an inertial frame that looks like this. Just like this. Actually, let me make that a little bit bigger. Actually, I can go like this. Let's make this a little bit bigger. Okay, and we need to define our unit vectors, right? So let's define this vector right here, and let's define this vector right here. And let's say that we're observing this right on one of the dimensions, so we're going to turn this into a two-dimensional problem, okay? Exactly, Vasily, you got it, man. We're going to call this vector the x-hat vector, and this vector the y-hat vector, okay? And then we're going to assume that gravity... not occurring at a slant. We're going to assume that gravity is occurring straight down in this direction at all times. Gravity is uniform. Now let's see. I was just making sure I have the right color here. Gravity is uniform. Cool. I know. I'm so glad that we finally get rid of him. I'm just kidding. But, all right. So we've defined our problem space, right? That's the first thing. Second, we need things called equations of motion. Derive equations of motion. And lucky for us, nice, Sai. I like it, man. Oh, you just got smacked back, man. Oh, Kelly coming back with a slap. Oh boy. Sai, you should try to get it to only set for you. That'd be funny. Guys, lucky for us, also, you're with them, aren't you? Yes, he is. How'd you get that copy? I just saw that, Kelly. Luckily for us, Elon Musk is willing to use his atmosphere destroyer. Atmosphere vacuum, which he has trademarked, to eliminate the atmosphere for the launch. How nice of him. He's donated the whole thing to us. So we can use it now. Which means that we have no atmosphere, right? So let's come up with the equations of motion then. Okay, that's not what I want to do. Page up and go over. Sorry about that. So, nice of Elon Musk to do that. Now we have all the information that we'd want. We have no atmosphere, but we have a uniform gravity field. So let's go like this. Let's set up the problem statement. Let's go like this. Let's get our inertial system back up and running again. Feline Musk. We've got a few things, right? Let's go like let's define our unit vectors. There's one of those going out right here, and then there's another one going out right here. Okay. Let's call this X hat and Y hat. Okay. Tagged word on Twitch? I don't know. Feline Musk. I like it. So, let's say that the object is somewhere in space, right? Let's say that our intercontinental ballistic puppy and kitten missile is right here in space. What forces are acting on this vehicle right now? What forces are acting on the vehicle? We've already said that Elon was willing to use his atmosphere vacuum, and we also had discovered that gravity is flat because so is the Earth. So, what vector and what direction should we add to this equation of motion? I hope not, Kelly. I sure hope not. Now, it's flat, obviously. Up, left, side to side. Nope, there's no sun. Earth is already warped way far away from the sun, and the sun we're no longer orbiting around the sun. The sun's gravitational pull does not matter. We're adding a gravity force, not to the side. We're having a gravity force downward, just like this. Okay, that's close enough. And we're going to call that vector G, gravity, okay? And now, right, let's say that we can lay out the trajectory of this thing. The trajectory is just the path through space and time. Well, maybe we should have the ICBM actually on the trajectory. And boom, it's going to land right here, okay? This is the USA, and this is Puppy and Kitten World. Puppy and Kitten World. Man of my dreams. Nice. We know one other thing, that we've got another vector that we can clearly see here, and that's velocity, right? Velocity. Boom. And this is velocity, okay? This is our velocity vector. So we know a few things, right? Let's take a look at this frame. I'm going to draw that right on the dot, right here. Just like that. All right, we know a few things, right? We know that gravity only works in one of these dimensions, okay? Just jump from one world to another? How? There's still gravitational pull of the Earth. Don't make me make more assumptions. I've made enough assumptions already. So the X is the Earth ground. This is the Earth ground. Y is going straight up. So we've got two vectors here. Note that G is only working in one dimension. One dimension. Right? So we know a few things, right? We know for A, the acceleration of the vehicle is equal to what? It's equal to g. That's the only acceleration acting on the vehicle. Only acceleration acting on the vehicle. That's the only one. Just like that. It's the only acceleration, so PKW is on Earth. No need of rocket. But you don't want to walk all the way there. We need to get these puppies and kittens there fast. Super fast. And we don't have cars that are fast enough to do it, so our only option is a rocket. That's our only option, Vasily. There's our only option to get there in time. A is the only thing acting upon it, right? So let's take a look at this then. We're going to do a few things. We're going to separate this out into components. That's something we can do in Cartesian systems. Cartesian equations can be separated into components. Components. Boom. Components. Yeah, this is Newtonian. Well, yeah, this is Newtonian physics because gravity is included. But not really, because I'm not using gravitational equations. And it's no problem. It's no problem, FleshY. No problem at all. It is the basics, Flesh. I mean, we started like basic, man. We started this lecture, for those of you guys that weren't here, with what is STEM. We quite literally started with what is STEM. And then we started with Aristotle, going way back and talking about philosophy. We quite literally started at the beginning. Okay? And we went through second law, for example. We went through second law and how to derive F equals ma. We went through the process of deriving F equals ma. We went through what reference systems are, like all of the reference systems that we're using. What is a Cartesian system? And then on the second line, we continued work there, and we talked about, okay, do we live in a Cartesian system? And now we're modeling an intercontinental ballistic missile that we're, oh yeah, no problem. We're modeling an ICBM that delivers puppies and kittens to Puppy and Kitten World. Okay, really? View, zoom, in. Okay, 100%. All right, we're good. It's no problem, Gilly. Into components, right? So let's take a look. We know this, right? We know that in that case, A in the x direction is equal to the gravitational vector in the x direction. We also know that AY is equal to the gravitation in the y direction, okay? But what else do we know, right? Does matter mean the element that counts? No, it just means no, Vasily. I mean, that's cool. I like that, but no, it's just like introduction, right? It's just introduction. But that's pretty neat, Vasily. I like that. I might use that. So we know that A is equal to G, but we know the components are separated out like this, right? So we can go like this. We also know that there's no gravity in a specific direction. There's no gravity in the x. No gravity in this direction. Which means that all of the gravity is in this direction. So, let's integrate, right? If we continue to integrate, then we get this. We get integrate. Integrate. And if we do that, we get the following. If we take the derivative of ax is equal to of 0, right? What does that give us? It gives us Vx, the velocity in the x direction, is a constant. Okay? So this is one thing that we have learned. Hey, we discovered something about this ballistic missile, right? We have discovered that velocity for our ICBM in the x direction is a constant. How cool is that? We're going to call this C1, the first constant, okay? Woo, integration hype. You got it, Vasily. Well, there is an atmosphere. There's an atmosphere. It's just that Elon Musk uses his atmosphere vacuum to temporarily get rid of it, you know, just until we get the puppies there. It's only temporary. So Vx is equal to constant 1. That's what we know, right? Then let's go like this. Let's integrate Ay is equal to the integration of G, right? What does that turn into? That turns into Vy is equal to gravity multiplied by time, because we're integrating over time, GT plus C2, right? C2. Check that out. So this is our velocity at any given time, okay? So it's a little bit different, right? This is a little bit different than Vx. So let's take a look at that then. Instantaneously. So at this point, the kittens and puppies are merged into a poodle of pink goo. Nope. We've developed impulse technologies. Thanks again to all of the science of Elon Musk that allows us to stay alive during impulsive maneuvers. There's a lot of awesome things that Elon's been doing. That is one of them, though. We do have the capability to do that now. I forgot to mention that in the assumptions. So this is the velocity at any given time, right? What is the velocity in the y direction at t is equal to 0? All right, this is called an initial condition. Initial condition. Okay? So it's teleportation. Yeah, it's teleportation. Use arc or Hohmann transfer. We can get... it's an arc. Well, it's an approximation. Can we do a more direct contestant burn? Well, you're always going to get more optimization by an exact finite burn that's constantly burning when you get there. That's the way to optimize that problem. But we're not going to do that. All we're doing is we're giving an impulse, a delta V, right at the beginning. So check this out. That means the best range with a 45-degree initial launch angle. You got it, Kyran. So let's go like this. At t is equal to 0. So if we set Vy at t is equal to 0 is equal to G at time 0, so we're going to plug in 0, plus C2. What does that mean? Vy at t is equal to 0 is equal to C2. Cool. So what we now know, to get ICBM to Puppy Kitten World. To get ICBM to Puppy Kitten World, we need a few things. We need to have an initial velocity in both directions. That's required now. In both directions. It's required. We cannot depend on gravity to get us there. Gravity will not get us all the way there. Can't depend on gravity. We can't depend on that g term there. Well, it's an ICBM with one impulsive maneuver in the beginning. Yeah, good thing they're strapped in. Nope. This is also it's a slightly different dimension, right? Where gravity is constant. It's a constant field all the way across. Gravity does not increase when you go upwards. The mass of the Earth is dependent on how far away you are from it, in a sense that the gravity is constant. So anyway, we now know this, that we need to give it an initial gravity. So let's give it an initial velocity. Let's give initial velocities. Oh, crap. Initial velocities v sub 0 in the x direction and v sub 0 in the y direction. Okay? Cool. Have to leave to continue winterization of the house and yard, but keep the good work. Sounds good, Kyran. Thanks for hanging out, man. It was a lot of fun. So let's take a look at, oh, come on. Let's take a look at our problem statement one more time. Now that we've more clearly defined the problem statement, once again, okay, let's go like this. Okay, we know that we've got our puppy missile. That sounds bad. That sounds so bad. We've got 2 dimensions in our problem statement. We've got the x dimension and we've got the y dimension. We know that there is gravity acting on. We know that there's gravity. We know that that this is the. Oh, actually, I want to do that in a different color. Excuse me. I want to do that in what color? In that bluish color. And we know that the rocket has a trajectory that looks like this. And we know that we want it to land in Puppy Kitten World. Puppy Kitten World, this is the USA right here. What else do we know? We know now that we need to provide to it an initial... Whoa. I'm going to draw this a little bit off so you guys can at least see the vector. This is going to be V0y. And this is going to be V0x. Okay? The next thing we want to determine, right? And this is going to have a velocity that does not curve with the trajectory. Well, it kind of will, actually. It's going to have a velocity at any given point like that. Okay? And now we've more clearly defined our equations of motion. Now we've got velocity, right? So now we have this. We've got let's keep our coloring consistent here. We know that v in the x direction at any given time is going to be equal to v0x. Why is that? Let's take a look. Because we've already determined that from this, vx is always going to be a constant, no matter what. All right. So it's just that initial velocity. Yep, vertical and horizontal velocity. You got it, man. Oh yeah, Vasily, I forgot the other I'm running out of assumptions. Vasily, just accept it. You need a roller slap. You need a slap on the back of your hand. Accept the universe for what it is. And then we've got Vy, right? Velocity in the y direction is equal to our gravity multiplied by time plus V0y. Okay? Yeah, Vasily, I'm cutting you off. You can no longer make more assumptions. Just accept the universe as it is. So we've got our equations for velocity now, okay? Lastly, let's try to come up with position. This is the last thing we're doing here. Let's make a new color. Let's do this fancy color here. Another useful term. Position over time, right? Position over time is something we would all like to know. So let's figure that out then. So let's just integrate velocity one more time. So we've got, to start, Vx is equal to V0x. Let's integrate to get this. Sx, which stands for position. It doesn't stand for position. That's what I'm calling it. Sx is equal to V0x multiplied by time, because that's what happens when you integrate a constant, plus C3. Okay? And then let's do the same thing with Vy. Well, actually, let's stay with Vy. dx over dt. Whoa, YOLO.